Hello, this is Jack Jackson. In this video, we're going to start a series of videos where we're going to examine different congruence criteria, or lack thereof, in various different geometries. So in this particular one, we're going to look at the side angle side condition in Euclidean geometry. Now, we're going to make use of some GeoGebra um, activities that I have created and some that some other folks have created. And I've collected these in a GeoGebra book called Geometry Collected Resources. And this 6 for week 6 or unit 6 in my notes, my course, uh, is where we have these. So 6A is triangles in Euclidean geometry, 6B triangles in hyperbolic geometry, 6C triangles in spherical geometry, and 6D triangles in taxicab geometry. So if you look here, we have several different things here. We've already talked about some of these things, looking at Euclidean triangles in general, classifying triangles. We've looked at some of these other things here and what we mean by defining triangles as being congruent. And today we're going to look at this one here, the side angle side triangle congruence criteria, and explore that in Euclidean geometry. And so we're going to open this in the app like this, which is the way I suggest you do this. So what we have here is we start with just a free point for a vertex that could be anywhere in the plane, and we're going to specify a side length for the first side, a second side length, and the included angle between those two. Okay, so let's take a look at this, and we're going to step through a construction here. So we start, step 1, we specify that first side length, the distance of, well, in this case, let's just make it easy so I can refer to it. I can type in, say, 10 here and say maybe 4 here. And the angle, let's just say 1.5 radians. Hmm. Okay. There we go. Don't want to delete the radian part of it. Okay. All right, so there we have something. We can enter a number here, or we can adjust it by doing the slider. Okay, so let's go through this. If we just slide this slider across, we can show the investigation. So we start by creating a circle of radius, whatever this is. Let's again, let's go back to 10. There we go. And then we can pick any point on that, and it is going to be a distance 10, and so that makes our line segment AB. Notice B is free to move anywhere around the circle. A is free to move anywhere in the plane. Next, we want to do what? We want to go out a certain angle. So this angle is controlled by this slider here, and we set it to where we want it to be. Or I can do it by by just typing it in. So we can set it to be 1.5 radians, which is about, a little bit less than 86 degrees. Okay, and you can actually put the degree symbol there and put in an angle in degrees if you want as well. Okay, so the question is, where is the point C, right? It has to be on this ray here somewhere for that to be there, but it also has to be on this circle, which is of radius 5. So how many places does that angle terminal side meet that? Well, the answer is just one right there. And so we get point C there, and that's enough to finish up the triangle there. And now we can measure the other sides there, and then the other angles. We could say if we had a protractor and a ruler, we could do the same thing. Now, actually, there was another option. Instead of the angle being up this way, we could have got the same measure angle by going here. Notice that these two angles both are 1.5 radians there. And then we could have made our triangle down here. That ray would meet this circle at exactly 1 point as well. I'll call it C prime. So there are two possible triangles here, but what I want you to notice is those two triangles are actually congruent. Not only do we have side itself, congruent, angle, congruent, and then side here, side, angle, side, it turns out that the other sides are congruent. The other angles, see if this one here, there it is, about 1.16 radians, or about 66.72 degrees. Same size angle, and then also the same size angle here. Both of these are measuring the same as well. So these two triangles are congruent. So it really didn't matter whether we chose the triangle down here or the triangle up here. They are congruent to each other. We can actually see that there are reflections of each other over this blue line segment, or the line containing that blue, containing A and B. Okay, so let's think about this a minute. Is there any way we could break this? In other words, is there any way we could come up with some set of measurements where there's no triangle possible? Okay, as long as we're talking about an actual angle, something bigger than 0 and less than pi, or between 0 and 180 degrees, a proper angle, and no matter what we pick for that first side, that first circle, it's going to intersect that one side of the angle in only one place. And likewise, the second circle is only going to meet in one place here. And really, it doesn't matter where we put it. These two triangles are reflections of each other. So really, no matter how we do it, we're going to end up with a triangle, and all the triangles are the same. Now, if we had a case where one of these triangles is not possible, we would say, well, there's 0 congruence classes for that. It's not possible. That's not ever a possibility here for the side angle side condition. Give me any legitimate measure for an angle and any legitimate measure for sides, and there's always a side angle side possibility for a triangle. But what we also notice is that no matter what you pick for those measurements, you're only going to get one congruence class of triangles. In other words, all those triangles are congruent. You know, if you build a, whatever, what do we want to do? Let's say 20, whatever units, centimeters there, and say 8 centimeters there, and a certain measure of an angle, say a one radian angle there, and I build it on my paper and you build it on your paper, they will be exactly the same. We can cut one out, take it over to the other one, and place it on top, and they'll match out perfectly. Yeah, we may have to scoot it over, we may have to translate it, we may have to rotate it, we might even have to flip it over, reflect it, but they will eventually match up. So what we found out is that no matter what you pick for the two sides and the measure of the included angle, whatever you pick for those three measurements, there always will be a triangle, and all triangles of that size will be congruent to each other. So there's always exactly one congruence class. And if you have two different triangles, and maybe you don't know what these measurements are, but you know they have a side angle side corresponding congruent and congruent pairs, corresponding congruent pairs, side, angle, and side, then the two triangles will have to be congruent. All right, let's look at another one. Here's another application here. Tim Brzezinski put this one together. This is taking a little different perspective, and this is instead of using the congruence definition that we've been using, which is that two triangles are congruent if and only if all 6 corresponding parts are congruent. That is, the 3 sides and the 3 angles are congruent. This is doing a more transformation approach. So it's basically saying, okay, we've got a triangle here. If we have a side there and a side there, and the angle is matched up, then the whole triangle has to match up as well. Okay, and so there could even be one that's reflected over, and it will be there as well. And this is, of course, it's dynamic. You can adjust the side, the angle, and the side. So that's another way of looking at the same thing. So we see that the side angle side congruence criteria is enough to make the the two triangles congruent. If you have two triangles and they match up side, angle, side, and congruent parts, corresponding congruent parts, those two triangles must be congruent. Also, if you're given any measurements, there's always one congruence class involved here, at least in Euclidean geometry. So let's investigate that now in the other geometries in the next couple of videos.